Today I'm going to talk about momentum. I know that's what the 18 and 16-week kids and a little bit of what the 4-week. So I wanted to work out some problems for you guys and just kind of discuss some common misconceptions. But before I do that, I'm going to go ahead and do housekeeping like I usually do, and just discuss with you guys some due dates coming up. So as always, we have a due date this Wednesday. Just for 81. Backwards in my head. Sorry. 10/18. That's Wednesday, so that's tomorrow. Everyone has a due date. Everyone has something due. Okay, so the 18 and the 16-week kids, you guys have your momentum test. Hopefully you watch this before you take the momentum test. It might help you, or at least maybe if you do corrections, you'll watch before you do the corrections. Or worst case, you at least do it after the test. You can fill out that momentum yellow, and then you get an extra point on the test. Even if you get 100 on the test, you can still get the extra points. You can get above 100, which can be really helpful. And the 14 students have a mechanical energy test. I reviewed for that the last 2 weeks, so please check out those recordings from the last 2 weeks for help for that. And then the 12-week students had their application of Newton's laws test. And I reviewed for that the 2 weeks before the mechanical energy test. So again, look for those reviews and hopefully complete the reviews or watch the reviews before you take the test. Not only will it help you review for the test, but it'll also, if you complete the ELO that goes with it, you can get extra points on your test. So that's kind of helpful. Next week, it's our last due date in October, which is crazy. That means we have, after that one, we basically have a due date every week but Thanksgiving in November, and then we've got like a week after Thanksgiving that we have, which is our last like full week of class, and then the next week is the final exam. So, we're kind of closing in on the end of the semester. So by next week, the 18, the 16, and the 14-week students will all be working on the same things, and they don't have any tests due. So that's kind of exciting for them. Use that time to get ahead, or do corrections, or maybe some ELOs that you haven't done yet. Use that time, because I think you guys only have a few assignments due that week. And then the 12-week students, again, you guys move a little faster than the other sections because you're doing 8 weeks of work in 12 weeks. You guys have your mechanical energy test and your momentum test due that week. So the review today will help you for that. And then review the previous 2 weeks. Those will help you for the energy test. Okay, so that's kind of the rest of October basically. And then really important, I'm going to write this really big on another page. It's on your newsletter and it's on the syllabus. On October 30th, that's a Monday, we will have our session. not Tuesday because of Halloween. So this session, October 30th, will not week of October 30th, we're not going to have a session on Tuesday. It's the 31st. It's in your newsletter, and I'll mention it again in the weekly update emails, but just to remind you, and it'll remind you in the course as well. Due to Halloween, we're going to go ahead and have our session on Monday instead of Tuesday. So I just wanted to kind of put that out there for you guys. Another thing, I'm getting a lot of questions. What can I do to improve my grade? Okay, I'm getting this a lot. Okay, there are a couple things that you can do. You can turn in work early. If you turn in your labs early, I can grade them. And then that doesn't mean turn it in Wednesday night at 10 p.m. That means if you turn in like Monday or Tuesday, I can usually grade, definitely Monday, but Tuesday, I can definitely, usually Tuesday, I can grade it and then give it back to you, and you can make corrections and fix whatever I said was wrong, and then turn it back in before the due date, and then you get, you can get those extra points. So turning in work early is a great way to raise your grade, or at least on time. Okay, most people that are asking me this are students that are turning in their work late. Okay, if you turn in your work late, you're just leaving points on the table. You're just throwing points away because you're losing between 10 and 30% each assignment. That's huge. Okay, so turn in your work early or at least on time. Okay, the next thing you can do is you can do your test corrections. Okay, if you haven't been doing those, go ahead and do them. I know some of you are waiting till the very last minute. You can do that, but it's really best to do them early because then you really know where you stand going into the final exam. If you wait and turn your test corrections in December 6th, okay, then you're not going to know exactly where you stand going into the final exam. So it's really important that you do your test corrections early. Plus, a lot of stuff we do builds on itself. So if you do the test corrections earlier, you may recognize a misconception you had, and then that would help you, on future units. So I highly recommend doing them early. The next is the synchronous sessions ELO. You can do them for each unit, and you get 1 point back on your test for each synchronous session. And you basically just answer a question, like work out a problem of the content that we discussed during that ELO. And if you watch the whole of the synchronous session, and if you watch the whole synchronous session, I work out that problem for you. Okay. And then you just turn it in the Dropbox folder. It'll say like the one for today, it'll say momentum, synchronous session, ELO, and then you just turn in your assignment there. It has a question that you need to answer, all of that. You just turn it in, and you get your points. The next thing I recommend doing is spending time with the content. And so what does that mean, spending time with the content? Let's talk about what spending time with the content means. Okay, it means reading the content pages in the course. Okay, it means doing the practice problems. And sometimes you may need to do the practice problems more than once. When I was in college, I took calculus. Um, Math is still not my strong suit, but I wanted a good grade in calculus. So I would do my calculus homework um, 2, 3 times. The first time I would do it, I would, have to look at the solutions a lot to kind of figure out how to work out the problem. The second time I could do, some of it, but not all of it. Still have to look at the solutions a little bit. And then the third time, I could just, I couldn't write out the work and the answer fast enough. Um, and so you may have to do it more than once, and that's okay. You want to get to the point to where when you see a problem, you're like, oh, I know exactly what to do. I can't, write it fast enough, because I know exactly what I want to do. Um, and that takes time. But, um, some people have to spend more time in physics than others. And that's just, the luck of the draw. You may be really great at English and have to spend a lot of time with physics. Other students, may really struggle in English and they just fly in physics. So it just depends. So you may have to put in a lot of time. The next thing is watch the recordings. Okay, watch these recordings. I work through problems. Um, I try and discuss any misconceptions I may have noticed throughout the week, the students turning in work, that kind of stuff. So hopefully these are helpful and I walk you through the problems where like in a practice problem, you've got the solution there, but you don't have anybody kind of talking you through it. I talk you through it as I solve it. And the next thing is look at the course resource newsletters. There's one for each unit, and then each one has information about each assignment. So if students have been asking questions about the assignment, I've got their question and the answer. I sent them there. That way everybody gets the benefit of those answers. I've got, if you scroll down to the bottom, I've got all sorts of additional resources. I've got videos that I've made. I've got videos from Khan Academy. I've got practice problems that I've made, additional ones from the ones in the class. I've got different websites that have help with the content. So all this sorts of stuff, and that's all there in the course resource newsletter, just waiting for you to access it. And the way you get to it is you just go to the course homepage, and then those colored buttons at the top, you just click on the colored button that matches whatever unit you're looking at, and it'll take you straight there. Okay, so that's also a really good resource for you guys. Okay, so these right here, these are the big 4 things that you can do in order to improve your grade. And the big thing is um, when you spend time with the content, do this before you take your quizzes and your test, not after. Okay, I get a lot of students that are turning in assignments, and I can tell that they've really not looked at the content. They're not, really, they don't understand the material at all. They're just like, oh, I need to do this quiz today, or oh, I better turn in my quiz so my mom doesn't yell at me, or whatever. And they just take a quiz and they just kind of like fly through it, or they'll do the test and they won't even attempt the short answer. And so you know, that's not a good way to improve your grade. That's a good way to make your grade lower. Okay, so that's really important. So now that I've talked about that housekeeping stuff, let's discuss momentum. So momentum, for some reason, the symbol for momentum is a P, and it's actually like a Greek-looking P, but I just use regular P because it doesn't really matter. But it's weird, and it's your mass times your velocity. Okay, so something with a really big mass could have a really big momentum even if it's going slow. Like for example, a semi truck. Right, semi trucks have huge mass, even if they're going really slow, they could still have a huge momentum. Another would be like a sports car. You could have a sports car that's not very heavy, and if it's going really, really fast, it could have a really high momentum. And the units for momentum, there's no special unit like joules or newtons or anything like that. It's just called kilograms times meters per second because your mass is in kilograms and your velocity is in meters per second. Okay. Then we have something called the momentum impulse theorem, or the impulse momentum theorem. And this is kind of what you guys have been discussing this week in your discussion posting. And I've noticed a couple kind of misconceptions here, so I want to kind of talk about that. So impulse is basically your force times time. This side of the equation is known as impulse. Okay, so your impulse is equal to your final momentum minus your initial. Okay. Now, there's a couple things you can do. I'm going to kind of talk about this in generic terms. So if you have a really large force in a really small time, okay, you could have a large impulse. If you have a large impulse, like in a car crash situation, it's going to really hurt. Okay. Now, if you have a small force and a large time, you could still have a large impulse, and but it's not going to hurt as much because basically this force, if you have like in this top scenario, you've got this large force acting over a very small time, and so that's really going to hurt. Okay, because you've got, like, for example, if you are traveling in a car and you hit a brick wall, that's a huge force, and it's going to happen in a very small time period. Okay, and then the other one, you could have a small force and a large time. Let's say that you're traveling in a car, and instead of hitting a brick wall, you hit like a bouncy house. I know that's a weird um, example, but bouncy houses are kind of squishy. So you hit that bouncy house, and so the time it takes you to slow down is going to be much smaller, or it's going to be much larger. Your time is larger, and so that's going to give you a small force, and so that's not going to hurt as much. It's going to be safer. Okay, so basically, maybe I shouldn't. I should just say that that's the impulse, and it's going to really hurt. And then large time is going to be safer. So, for example, these safety devices in cars that you guys have been talking about, a lot of them, the point of them is to increase that time that force occurs. Okay, so like an airbag. Okay, same kind of thing. It's going to increase the time it takes for you to slow down. The crumple zone in a car, again, increases the time it takes for your car to slow down. Um, what was another one that I've seen you guys talk about? Um, saw something about self-driving cars, seatbelts. Okay, the seatbelt, same kind of thing. The seatbelt is it's gonna keep you, it's gonna slow you down a little bit. Instead of, you're gonna fly through the windshield, and hit that brick wall that you're hitting the brick wall. Instead of hitting the brick wall or flying through the windshield, that seatbelt is gonna kind of, you've seen when you apply the brakes, those seatbelts kind of get tightened up, and that's going to keep you from flying somewhere. Okay, so that's kind of how impulse works. Okay, and we'll do some problems with impulse. We'll kind of, hopefully, you guys will actually get to see um, what I'm talking about with the impulse and hitting a brick wall, let's say, versus like gently, um, the brakes, instead of hitting something or whatever. So impulse is basically the change in momentum. And here they are. They're talking about the airbags here. Okay. So And they're saying the airbags is taking the force occur over a larger area of the body, so it's gonna slow you down. Okay. Um, so let's try a practice problem. Okay. So in this one, we've got a few things going on here. Okay, so we have a 2,200 kilogram vehicle. That's going to be our mass. Is traveling at 94 kilometers per hour, and then they're actually nice enough to go ahead and tell us the meters per second. So that's going to be our initial velocity. So I'm going to call that V0. It says it can be stopped in 21 seconds by gently applying the brakes. So I'm going to call this T gentle. And then it says it stops in 3.8 seconds if the driver slams on the brakes. So I'm going to call this T slam. Or in 0.22 seconds if it hits the wall, concrete wall. So I'm going to call this T wall. Okay. And then it says, what is the average force, or what average force is exerted on the vehicle when the driver gently applies the brakes? So we're looking at the gently applying the brakes part right now. Okay. So the first thing I'm going to do is I'm going to write what I know. Okay. Now, one thing I noticed is that I don't have anything underlined for my final velocity. Do you guys see that? We've got a V0, we've got a lot of T's, F, no, I mean VF. Okay, well it says the vehicle traveling at 26 meters per second can be stopped. Okay, stop tells me that that's my VF. My VF is 0. When you're stopped, you're not moving. Okay, and then I want to know my force. Okay, so for this one, we're going to use our impulse momentum theorem. Okay, now there's a couple ways you can do it. You can rearrange before or you can rearrange after. For this particular type of problem, I like to go ahead and rearrange after. Um, so I'm just going to plug in my stuff right now. And then I'm going to write this just so we don't forget. Impulse is momentum times velocity. Okay, so it's my final minus my initial. Okay, so that's 2,200, got an extra 2. 2,200 is 0 because that's my final velocity is 0. So it should be at minus 2,200 times 26. Okay, so this 2,200 times 0 ends up being 0, right? It doesn't count. So anything times 0 is 0. And then this ends up being 57,200. And I'm just going to divide that by 21. I'm going to write it over here so it's not real small at the bottom. So my force is equal to 27, 23, 81. Okay, so that's my force. Okay, now this is my force if I'm gently applying the brakes. The next one we're going to do slamming the brakes, and then the next one we're going to do concrete wall. So you guys can really see how this force just really increases with this smaller, as the time gets smaller and smaller. Okay, so let's see. We've got our 2,200 kilogram vehicle, that's our mass. We've got our 26 meters per second. It's our initial velocity. We've got stopped. Right, that's our final velocity. It says 21 seconds for gently applying the brakes and stopping in 3.8 if we're slamming the brakes. All right, so I told you we're going to do slamming next. So we need T slam and then the 0.22 if we hit a concrete wall. And then we're going to get that average force. Okay? And then here it is, slamming on the brakes. Okay? So let's write what we know again. The V0 is the same. You notice everything is the same except for that time. That's the only thing we're changing. And the way we're changing that time in this particular accident or this particular scenario is whether we're gently applying the brakes or we're slamming the brakes or we're just hitting the brick wall head on. Okay? We use the same formula, the impulse momentum formula. Okay, and I purposely chose this one problem with 3 steps because I wanted to show you guys what that impulse looks like, um, how that changes. Remember, momentum is your mass times your final velocity minus your mass times your initial velocity for a change in momentum. Okay, I wrote V0 before, so I'm just going to put 0 there to maintain the consistency. We have our 2200 again. Our final velocity hasn't changed, it's still 0. We have 2200 here. We have the same initial velocity as well. And so, this number that we calculated is the same. Okay, the only difference is the time that we're dividing it by. Okay, so the 2200 times 26 was 57,200. Instead of dividing it by 21 seconds, we're going to divide it by 3.8 this time. Okay, so that's much smaller. So our time is small, right? Remember, when we have small times, we're going to have, if everything else stays the same, we're going to have the same force. And so that's really going to affect our force. So in this one, our force is 15,052.63 newtons. Okay, last time it was 2,700 newtons, and now it's 15,000 newtons. Okay, that's a huge difference in force from slamming on that brakes as opposed to gently applying the brakes. Okay, and now we're going to try and see what happens, what it looks like when we hit the concrete wall. Okay, we're not putting on the brakes at all, we're just hitting the concrete wall head on. Okay, this I've known this to happen to some people. Say they fall asleep driving, you might hit a concrete wall head on, or if they've been drinking and driving, they may not be paying attention. And then some people, they just speed really fast or not paying attention. Maybe they're texting and driving, and they just hit something, maybe not a concrete wall, but a tree or anything like that, just full on, and it's devastating. Okay, so that's kind of what's going on here. So we have our mass still, we have our initial velocity, the final velocity is still stopping, and then the time we're going to use is this T wall, right? He's hitting that concrete wall, and then we still are going to look for the force. Okay. And these are not to scare you, but they're a little bit to scare you. I feel like this unit, it's really important to show you guys, what can happen in a car accident. When I taught in a face-to-face classroom, when we taught physics for a whole year, we tended to get to this section right before Christmas, and so we would talk a lot about, what would happen if you got in an accident, like drinking and driving, you're not using your seatbelt or whatever. Um, and in those conversations, I was kind of hoping to scare the students into not doing things like drinking and driving and things like that, since we were going into the holidays and the parties and all that kind of stuff. So we would use an example like this as well. Doing that, and we would watch lots of crash test videos and stuff like that. So I'm going to put the time in here, but instead of the 3.2 or the 3.8 or the 21, I'm going to do 0.22. So that's a teeny, teeny, teeny little force, or a teeny, teeny little time. I'm going to use this, everything else in the formula stays exactly the same. Okay, the mass is the same. The, the velocities aren't changing. The only thing that change is this time. Okay, so we've got 2200 is our mass. The initial velocity is 0. We've got 2200 is our mass, and our final velocity, sorry, our final velocity is 0, and our initial velocity is 26. Getting backwards. We're still going to cross out that 2200 times 0. So again, everything's the same. The only thing we're changing is that instead of dividing 57,200 by a large number, we're going to be dividing it by a really, really small number because our time is really small. And so that's going to give us a really big force, which is going to be really dangerous if you're the one in the car experiencing this force. So this ends up being 260,000. Okay, that's huge. Okay, so if we're gently applying the brakes because we're paying attention when we're driving and we see what's going on and we see traffic or we see the wall coming or we see a tree coming or whatever, it's only 2,700 newtons for the force. If we're not paying attention and we just hit that concrete wall going full speed, we're going to be experiencing 260,000 newtons worth of force. That's a huge amount of force. And that's why these car accidents, when people hit head on and they're not paying attention or they fall asleep at the wheel or whatever it is, it's really dangerous because, they're really getting hurt. They're experiencing so much force. So now let's talk about conservation of momentum. We have two types of collisions. We have elastic and we have inelastic. I end up usually calling elastic collisions not sticky collisions because it helps me remember what's going on at the end. See how they're separate at the end. Got this guy and this guy. They're riding off into the sunset separately. And then inelastic collisions, I call those sticky. And this is because they're together. They have the same final velocity. They stick to each other, and they ride off into the sunset together. Okay, so that's kind of how I delineate those. Now let's talk about um, elastic versus inelastic collisions. Okay, so an elastic collision, you're going to have no loss of KE. And it's not sticky. So afterwards, these two guys are separate. They go their own ways after the collision. They kind of hit each other and bounce. Okay, like pool balls. If you've ever played pool, when the balls hit each other, they bounce off each other. Okay, so that's that type of a collision. Now, an inelastic collision is when is a little bit different. You're going to have some kinetic energy lost to the outside environment. And this is considered a sticky collision. So a lot of times in class, when we discuss these type of collisions, they'll say like one ball of clay hits another ball of clay, and they stick to each other and they ride, and then go off together. That they call those types of sticky collisions. Okay. in some collisions where you've got like I've seen where like a semi truck hits a little car and the car like sticks to the semi or gets stuck under the semi and they go off together. That is also an inelastic collision. So if they're going off together, it's an inelastic collision, and if they're ending separately, they're going their own ways afterwards, that's considered an elastic collision. Okay. And they might have a question that says, like, which type of collision has no loss of kinetic energy? I've seen questions like that. And then you would say, oh, that's an elastic. Okay. So now let's try and solve a conservation of momentum problem. These problems aren't super difficult, I would say, but they are kind of tedious. They do require you to kind of slow down and just pay attention to what you're doing and just write the formula and just kind of go through it. You don't want to rush through these type of problems because you'll make a mistake. Okay, so in this one we've got a car that has a mass of 1875 and it's going 23 meters per second. Its initial velocity. And it's rear-ending a car that weighs or has a mass, excuse me, of 1025 kilograms, and it's going 17 meters per second. They tell you it's going on ice, and that's because they don't want you to worry about friction or anything like that. And then it says the two cars stick together at the end. Okay, that's pretty important. That means they'll have the same final velocity. And it says how fast do the cars move together immediately after the collision. Okay, so how fast means we want final velocity. Okay. So let's write what we know. We know the mass of our first car is 1875 kilograms. And we know our first car was traveling 23 meters per second. Okay. Now this car is hitting a compact car that is going 17 meters per second. And then it sticks together, so they have the same final velocity. Okay, so you can remember what we had on the previous screen, or I'll go ahead and write it for you. So we want our initial velocity or initial momentum of the first car plus the initial momentum of the second car equals the final momentum of the first car plus the final momentum of the second. Yeah, I know I put an I here. It's zero, maintain consistency. Okay. So then we have N, A, E, A, 0. And this is a step that people usually skip. And if you skip this step, you're more likely to make a mistake because you're more likely to put in the wrong. Okay, now this says they stick together. So this means they have the same final velocity and their mass. So it's their velocity, their final velocity is multiplied by the mass of the first one plus the mass of the second one, okay, because this is basically one thing. Okay, so now I'm going to throw my numbers in here. So I'm just throwing my numbers in here. And then I'm going to do 1875 times 23, which is 43,125, plus my that initial momentum of the other one. And I'm going to add these two masses together. Okay. And I'm going to add these two initial momentums. I'm going to divide those sides by 2100. Okay, and then where my answer. That's one thing about these conservation of momentum or the conservation of energy like you did last unit. You guys can see that this is kind of similar. They take up a lot of space. And so a lot of people try and skip steps because they take up so much space. But I've noticed that when you skip steps, you make mistakes. And I don't want to do all of this work and then make a mistake. So I just, I write all my steps even though it's annoying. But a lot of people try and skip this step. I highly recommend not skipping this step. Okay. Keep doing it. I know it's annoying to write all the letters twice, but it really does help, I think. Okay, so the two cars will ride off in the sunset together, going 20.88 meters per second. And if you look at that, the first one was going 23, the second one was going 17. So we're basically going, something in the middle, which kind of makes sense. Okay. So let's try another conservation momentum problem. And the reason I like to do this one is because it's just very different from a lot of the ones that we talk about. Because a lot of times when we talk about momentum, we talk about crashes and collisions and things like that. And this problem is very different because we have two things that are starting together and they're ending separately. So it's kind of like a reverse collision because they're together at the beginning and then they're ending separately. And sometimes when students see questions like this, they kind of freak out because it's just so much different than anything that they've kind of seen before, because they're expecting a collision and it's not. So I like to kind of do a problem like this. Okay, so if we're at rest, that's going to be our V0. We're starting at rest and we're firing a pistol that expels 35 grams of hot gas. So I'm going to just call this the mass. I'm going to call it B for bullet, even though I know it's not a bullet, it's hot gas, but it's, I'm just going to call it that because it's just easier. And then they're at 875 meters per second. So that's going to be the final velocity of the bullet. I know it's gas. The combined mass of the astronaut and pistol is 84 kilograms. So that's just my trying to eraser. Um, so this is going to be my M, A, B, or my astronauts. Okay, and it says how fast and in what direction is the astronaut moving after firing the pistol? So what the final velocity of the astronaut. Okay, so I'm gonna write what I know here, and then I'm gonna kind of draw a picture because it helps me just kind of visualize what's supposed to be going on. Okay, so my initial velocity is 0 meters per second, and this is the initial velocity of the bullet and also the astronaut because the astronaut's at rest and the astronaut is holding the pistol that has the little gas bullet or whatever. So they're both at rest. Okay, and then the mass of the bullet is 35 grams. And before I do anything else, I like to just go ahead and convert this to kilograms so I don't have to do it later. Zero point zero 0.03. Okay. Then the final velocity of the bullet is 875 meters per second. Our mass of our astronaut times our bullet 84 kilograms, which means the mass of our astronaut is 84 minus 0.035, which would give us 83,965. Okay, and then we want our final velocity of our astronaut. So I'm going to draw the picture, and then I'm actually going to see, I think I'm going to try and write the problem out on this whiteboard down here, just so we've got all that extra space. I don't want to try and squish everything here. Okay, so we've got our astronaut, okay, and then he's firing the bullet. Let's draw a little gun. That's the best I can do for a gun. Okay, and this little ball of gas is going to go that way. And then the astronaut's going to experience basically some recoil, and so he's going to go backwards. And so I'm going to say that the mass or the speed of my bullet is positive, which should mean that the speed of my astronaut is negative. Okay, so if I don't get a negative answer, I want to kind of figure out what's going on, because my astronaut and my bullet shouldn't be going in the same direction. One should be going forward and one should be going backwards. Okay, so I'm going to keep this 875 positive because that's going to be the velocity of the bullet. Okay, so let me go to this page, and I'm going to write, I guess I'll write in blue because it shows up pretty well on the white screen. Okay, so I'm going to write my formula. Okay, so my momentum formula is PA 0 plus PB0, right? The momentum of my astronaut, my bullet, equals the final momentum of my astronaut plus the final momentum of my bullet. Okay, now we are starting together. So you could do like, you could do something like this. You could do something like this, which, can you see how that kind of makes it look like the opposite of a sticky collision? It's like a backwards sticky collision. Because they're starting together, they're ending separately. But if you didn't want to, you could do them separately. Because you're going to get an initial velocity, 0 anyway, so your whole left side's going to end up being 0. Okay, so you see how I took this extra step to go ahead and write this part. Okay, that's where I said a lot of people try and skip that and they make mistakes. So our initial velocity is 0 times 84, right, because the mass of both was 84, equals the mass of the astronaut, which we found was 83.965. That's the final velocity of the astronaut, which we don't know that. That's the point of the problem, right? Plus the mass of the bullet, or a little gas, with gas, or whatever you want to call it. Okay. This is going to cross out, and our whole left side is just going to be 0. And we'll have 83.965 EF VAF plus 30.625. You have to minus both sides by 30. I'm going to pull this, I'm going to make this big. Uh, this, I made this mark here. It's confusing. So then we have negative 30.625 equals 83.965 VAF. Okay, and I'm going to divide the 83.965. Okay, 36 meters per second equals V. Okay, negative. Okay, so this, a couple things about this answer. One, it's really small, but that's okay because the bullet is going so fast and it's, weighs a very, or has a mass, very small mass. The astronaut has a very huge mass compared to the bullet, and so it's going to have a much smaller velocity in order, for those to be equal. The other thing that we need to notice is that our velocity was negative. Okay, now if you notice in our picture up here, we said that we wanted the astronaut's velocity to be negative. Okay, so it is completely makes sense. It's exactly what we wanted for this negative velocity for the astronaut. So that lets us know that we did the problem correctly. Okay, and so that is a different type of conservation of momentum problem. Okay, these are very similar to the conservation of energy problems. And again, you just need to kind of like slow down and take your time. That doesn't mean spend like 10 minutes on the problem, but it does mean that you want to, a lot of students, like I said, they like to skip steps, or they'll just go straight from like this step to this step, and this first, like we call this step 1, 2, 3, 4. I like to go from like just step 1 to step 4, and there it's really easy to make a mistake that way. So I highly recommend conservation of momentum and energy um, to take all the steps to make sure that you're putting, and I also like to write what I know. That way, when I am putting stuff in the formula, I'm putting VA here, I'm putting MA here, MB here. It's annoying, but at least I'm putting exactly what I want in the right spot so I don't make a mistake. So those what we discussed today were really the key points for momentum. So I'm going to put this here just to kind of, you guys can in the day seeing this.